All right, some of you are asking about and struggling with these hard ones from the university physics book. And yeah, let me work through this one. This is just another hard one. All I can say is chapter 18, one of the hardest chapters of this semester. And then it was the first one. And that's just hard in its nature. And then, of course, in the harder book, it's just even really hard. However, this problem, let me encourage you to look at my video solution of number 83 and 84. It's in the supplemental lecture because that's really what I'm going to springboard off. In 83, I did the electric field from a rod of length L. I think we were a distance A away and length L. And I would say that this problem is exactly like that, at least in part. It's just our length goes to infinity now. And we're looking at the field here at O, so we're going to go from a distance of R out to infinity. So that's the difference, plus you got a second rod. But what's nice about this and the strategy here is we'll get the electric field from one rod and then just have to say, well, it's the same for the other rod. Okay, and then we've got to combine those two fields. And then in 84, we did a half circle. I guess I would say now we're going to do a quarter of a circle. And so again, we'll do 84. But then we have to combine all those together. So we've got an infinite rod, so it's like 83, but twice. And then we've got a quarter of a circle, so it's like 84, but really half of it. Then we got to put all that together. So we got a lot of work ahead of us, but let's give this a try. The question is, then, I'll read it here. A positive charge is distributed with a uniform density of lambda. So everywhere where there's charge, we have lambda. And it goes from R out to infinity on the x-axis, and it goes from R out to infinity on the y-axis, and then it has this 90-degree arc that has radius of R. And then we're asked to find the electric field. So again, let's break this into the three parts. Maybe since I'm going to hopefully say I hope you watched number 83, let me do this a little quick. Let me find the electric field. I'll just go along the x-axis and kind of in my mind imagining, and I'll draw the field in green, but a little chunk right here that makes a field. So I'll call that a little chunk dq, and another little chunk, and another little chunk, and another little chunk. And so each of these make a field. And in this case, it would point in the negative x-axis, but not worrying about the negative, just the fact that what it is I would just add them all up. And so I would say a little bit of field, so call it dE, is really made up of a little bit of charge. And so this comes, again, as we hopefully you saw in 83, where this is the equation for the electric field. Okay, so then if we add it up, we add up all these little fields. The integral of dE is E. And then we can replace this dq, and so the definition of lambda is a charge per length. And so if I take a little bit of charge divided by a little bit of length, I get my lambda. And of course, where that's useful is then when I bring the dx to this side, my dq then is lambda times dx. And so that's how, if you remember in 83, I talked about how to change a dq into a dx. And then the distance away is just your value on your x-axis, so that's just dx. And so there's our integration. And like any integrals, kind of the first thing to always do is to say what are constants and bring them out in front. So we've got an integral. And fortunately, it's not a too hard of integral. And then the limits are from a out to infinity. Okay, so I'll have kq. And if you think about this as x to the negative 2 dx, you add 1 to the exponent and divide by that new one, and then take your limit of r to infinity. And I guess we would get something like this. I'll put the negative 1 over here. I'll think of this x to the negative 1 as 1 over x, so I have 1 over infinity for the upper bound, minus then a 1 over r for the lower bound. And 1 over infinity is 0, so I'll cross that one out. The two negatives cancel off, and you get k times lambda over r. So that would be this electric field at the point O from this long rod. So maybe I'll just draw kind of a solid green one up here and say, okay, that's the value of the electric field at O from all of these plus charges. Now, I'm just gonna make the same argument on the y-axis, so I'm just gonna put another one like that. And I'll have to combine them together. And since they're equal and at 90 degrees, the result is going to be at a 45 degrees. And if you remember a little bit about your 45 right triangle, you know, if you have two legs, the hypotenuse here is the square root of 2 times that. So I would say that right now, the value of the electric field is the square root of 2 times the electric field I get from just one of them. In fact, maybe that's worth kind of pointing out again, that if I have an A and another length A, then how long is the hypotenuse? Call it C. And we have a squared plus a squared equals c squared, which is why you get a 2a squared equals c squared, or c is the square root of 2 times a. And so that's our standard 45 right triangle. Okay, so I've done what I would say, I don't know if that would be the easier part, but the part that kind of go along with number 83, and I've just done it twice, but of course they're vectors, so I got to put those together. All right, so there's half of it. Now the other half is to do this quarter circle, but watch this, and maybe I'll turn it on the page so it kind of looks like this. If you kind of look at this quarter circle and split it down the middle, you're going to see this symmetry on each side. So a little chunk of charge here makes a field off in this direction, and a little chunk here makes a field off in this direction. And if we kind of have I'll call it an interesting grid, maybe I'll do it in black so it stands out, but if I do like that, and I'm trying to say then, because of these charges being symmetric, they're going to cancel off on the x-axis. And the result of this circle down the middle is also along a 45 degrees. And that's really great, because I've just said that these two are along a 45, and so now I just have to add another vector that is along a 45. And nothing is better than adding two vectors in the same direction, because that's just scalar. You know, it would be like adding a 3 and a 4. If 3 and a 4 are in the same direction, you get 7. It's harder when 3 and a 4 are at some angle. 90 degrees isn't too bad, because 3 and 4 at 90 degrees is Pythagorean's theorem. It comes out to be 5. But at some other angle, you got to break it down to its components, and the problems get kind of long and tedious. It's one student was telling me, because I finally finished 18, but it was tedious. And yeah, I remember doing one of the videos, and it was just tedious. It was kind of long there. I think that was 24 now that I think about it. I think that was one I sent you. But this one, fortunately, then won't be tedious if you see that. I'll just have to figure out what the strength of the field is along this diagonal here, and then just add it to this one, the value we got already. All right, so I'm going to just kind of put this on the back burner, if you will, and say, okay, I already know what the value and the direction of the electric field is from these two infinite pieces. Now I want to do kind of a quarter of a circle here. All right, and maybe let me just start fresh here. Let me kind of set up a grid in a traditional way. And maybe you can see it a little better. So this is the y-axis and this is the x-axis. And I'll come out here some distance r and distance r, and there's my charge making a quarter of a circle. And so this is 45 degrees, or let me write it as pi over 4. And then this, we might, I don't know if you want to say a negative pi over 4. Okay? And so adding, the two together is a quarter of a circle, pi over 2. Okay. But I'll say it again. And I think it's a little bit easier to see now in this drawing than this mess I was making earlier. But if you start off with what I call the symmetric twins, you look at a little chunk of charge over here, dq, and a little chunk of charge, dq. This would make a field in this direction, and this would make a field in that direction. And they would each have a magnitude of what I'd call a dE, okay? But again, hopefully you can see that this would be made up of a vertical component and a horizontal component. And then likewise, this would be made of a vertical component and a horizontal component. And my argument is the horizontal components, that is, if I take the dx components and add them together, you're going to get 0 because of the fact that you've got them equal on both sides. You've got this symmetricness about it. That's a word. You've got this symmetry about it. And so they cancel off. And then also, better still, and again, I'm going to trust that you went through 84 with me. After I did that, I said, well, we can only do the other half and double it. And that's what I'm going to do here. And so let's just then note that the vertical component in this picture is actually then this part of the circle. So I guess that's an eighth of a circle. And then I would double it for that size. So I'm going to do this. I'm going to say, let's add up all the little electric fields in the y direction. And that's going to be EY. Okay? And as I just said, let's only add up from a 0 angle to a pi over 4. And so we're only going to do this half of the quarter circle. So 1/8 of the circle, and then we'll double it. Okay, so there's the doubling, and then there's the eighth of a circle. Okay, and then again, the integral is exactly the same as we did in 84. And so, all right, I'll go 2, and I'll put the limits here. But this dE is, or dEY is the magnitude times, and so again, if you kind of imagine this sticking out with some angle theta there, which would make a theta here, it would be this cosine theta. And so that's easy to miss. And if you've only done this the first time watching my 84, you might have missed that, because it's really easy to confuse. What do I mean here by the component of that versus the magnitude? So this is the magnitude, and that's why when you multiply the magnitude by cosine of theta, you get the component dy. And so that's a big step there. A hard one to see. I think much harder than just saying, hey, I'm going to double it. Or even harder than just saying, hey, it's symmetric, so it's going to give you 0. Okay. So continuing on here, I've got a 2. And again, I'll just put my limits of 0 to pi over 4. And then this is Coulomb's constant times a little bit of charge, dq. And then the distance away, r squared, and then cosine theta. Now, like I said in number 84, what's nice about this one is that because we're along an arc of a circle, the distance away doesn't change as we add them all up. So I could pull out not only Coulomb's constant, but also r squared. And then I just have the dq and the cosine theta. And like we did for 84, and even we did on the first half of this, I'll come back here. Remember the definition of lambda. Lambda is a little bit of charge over a little bit of length. Now, in this case, since we're doing an arc, why don't we say it's dq over ds? Because s is kind of the traditional symbol for the distance along an arc. So we would have lambda ds equals dq. All right, and so that allows me right here, dq, to put lambda ds cosine theta. Now also, like we did in 84, this is nice, remembering that the definition of an angle in radians is the arc length divided by the radius. Or rearranging this, arc length is r times the radius. And then taking the differential, ds is then r d theta. And so now I can come over here and take the lambda out and replace the ds with an r d theta. Okay, and make the same argument that we did back in this step, that for a circle or a part of a circle, r doesn't change. So I can pull this out, which would make it cancel off with 1. And then fortunately, after all of this kind of analyzing, what I like to call reading the math, not really doing the math, trying to understand the math, we've got a very easy integral to do. It's just the integral of a cosine function. And that might be then what I said in 84, that maybe that's a little too much because where do I draw the line in the calculus level? Not sure. But I like to just give you power functions, and so the straight lines were good, but integrating a cosine might be a little much. And especially that, what was that one I did? 87, wow. Okay, so that had a cosine in it, it had a distance in it, it had a lot in it, and so you had to kind of do a lot of substitutions to solve that. Unfortunately, it came out to be an easy integral after we eventually solved it. It came out to be this integral, actually. But it was a little too much. Unfortunately, this one's not that hard to get here. But once we do get here, we need to say, well, what is the integral of a cosine function? And it's a sine function. Maybe you remember it better the other way around. If you have sine and you take its derivative, you get a cosine. So if you have a cosine and take its integral, you will get a sine. Actually, I may better think about that. Did I do that right? So there's a sine. I take its derivative. I'd have a 1, and then a 0. Yeah. So derivative of sine is cosine. So integral of cosine is sine. And so then we would evaluate it from 0 to pi over 4. Okay. So we've got a 2k lambda r, and then we have the sine of pi over 4, which is the same as the sine of 45 degrees, which is that magical 45, 45, 90-degree triangle. And so this is root 2 over 2. So I'm going to replace this with the square root of 2 over 2, and then the 2's cancel off. And so I end up with the square root of 2 times k times lambda over r. And interesting enough, if you come all the way back, that is the value we got from the two straight lines. And like I was trying to say earlier, the two straight lines give you this, and now we just have shown that this quarter of a circle right here gives us that same amount, and they're in the same direction, so the total is just to add them together. And if you add them together, that since they're the same, it's just the same as doubling it. So it's 2 root 2 k lambda over r. And there you go. There's the solution to that hard one. And again, I can't say this enough when it comes to electricity and magnetism. It's not just doing the math, but it's really reading the math. Half of this was done really with a picture of looking at like its symmetric twins. It was looking at this and saying, wow, this looks kind of complicated, but how can I divide it into 3 manageable pieces? So there's a lot of visualization. And of course, right here, how do we get a little bit of electric field? Well, we get it from a little bit of charge. Then, you know, there's all kinds of things here. How do we get the, you know, the little bit, the y component of a little bit when we have the little bit magnitude, we multiply by cosine thing. So all these little things that what I call reading the math and understanding the math, interpreting the math, not just doing the math come into play. So we have to do the math too, and that's by itself is hard. But then we also have to read the math. We have to kind of digest that. All right, hope this is helpful to some of you, but I will say this again is another one of those ones that it's just over the top hard. I probably shouldn't have even assigned this one. This is a little too much for this class and this level. It's just I know this class is supposed to have a little bit of calculus in there, and this is how we approach it. We have the book with the non-calculus, and then we kind of throw a few problems in here with the calculus. But sometimes, like this material, it's really hard to find any that are just a little bit of calculus. They often have just either no calculus or a lot of calculus. All right. Take care.